Hello everyone. First of all, I would like to thank the organizers of the conference for giving me an opportunity to share my thoughts on the topic Advanced Optical Metrology in Material Testing. My name is Akshat Agha and I'm a Materials and Development Engineer at FADI AMT in USA. Let me start with a quick bio of myself. I did my mechanical engineering from BITS Pilani in India, graduated in 2013, and then I joined Honda Motorcycle and Scooter India for 2 years before I moved to the US for pursuing Masters and PhD in Automotive Engineering. After graduating in 2019 with my PhD, I've been working as a material testing and development lead at FADI AMT LLC in USA. The prime goal of my research has been to achieve a greater utilization of lightweight materials through advanced material testing, material modeling, and FEA implementation, primarily focusing on the materials that cater to transportation sector. This slide shows some of the tests and the work that I have done in the past, which involves material testing coupled with digital image correlation or DIC, which is the topic for today's presentation. So let's move on to it. Today, we'll be talking about digital image correlation, what it is, what it can do, its application in material testing. Then we'll talk about how does it work, and we'll top it up with some creative applications of DIC with the final remarks. So let's begin with what is digital image correlation and what can it do? Digital image correlation is an optical metrology tool. It can simply be taken as an image processing technique which can be used to analyze a set of pixels in a series of images that were acquired during the deformation of an object. This technique can analyze those images and spit out the displacements and the strain fields in those images. There are a few examples of the application of DIC technique given on this slide, and we'll go into further detail in the upcoming slides. Here is a video that shows the different applications of DIC in diverse fields. First is the strain measurement in a material test, followed by vector displacement measurements for a crash test dummy. This is a commercial goods strain measurement, followed by fracture measurement in civil engineering. Let's see what DIC means to us in the material testing world. The simplest example of a mechanical test on a material is a uniaxial tension test, or simply called as a pull test. I'm sure all of us have at least witnessed a uniaxial tension test at least once in their lives. Most likely it was in the first year of engineering when we were made to sit in front of a big giant machine, something called as a universal testing machine or a load frame, as shown in the image here, where the technician was pressing some buttons, pulling a sample, and trying to generate a curve which looked something like this in this image. This curve, called as the stress strain curve, is the basic mechanical property or the result of a basic test that defines the general behavior of any material in response to external strain. Conventionally, a stress strain curve is obtained by the force coming from the load sensor attached to the top axis or the crosshead of the machine, and the strain is obtained by the LVDT sensors that are also attached to the machine. To increase the accuracy of strain measurements in advanced material tests, there came something known as clip-on extensometers. So these extensometers latch on to the sample directly and give a 2-point measurement of the strain. So these extensometers are supposed to extend as the sample extends and give out the accurate strain measurements directly from the sample. Now comes the state of the art in material testing, that is digital image correlation. How does that work or couple with material tests? In the picture in the middle of the slides, we see a set of cameras looking at the specimen while it is deformed. This is a commercial 3D DIC system that is observing the specimen or recording images while the specimen is deforming, and these images are later used to analyze the strains on the sample. Let's look at an image, or sorry, a video that shows the true power of DIC in a uniaxial tension test. So this video is a DIC generated video that shows a tension sample extending in the upward direction and the strain contour evolving on the surface of the sample. The top right plot shows the extensometer in the vertical direction as well as in the transverse direction. The bottom right plot is a typical engineering stress strain curve. Now this video, which I'll play again for you, shows something very specific to aluminum alloys 5000 series. This behavior is called as PLC banding. As you will see, when the deformation happens, it's not really homogeneous. It's in steps, and these bands of localized strains move through the specimen from top to bottom and then from bottom to top. This kind of behavior, when shown by a material, is only shown by digital image correlation, and a typical contact extensometer cannot really show the true nature of this material. Let's see the video again. You'll see bands of strains moving from top to bottom, and then the strain starts localizing and the sample fractures. So overall, DIC truly has transformed the way we characterize material deformation and failure. For today, we will try to focus on the unique side of DIC and highlight particular areas in material testing where DIC can truly transform the way we characterize materials and understand their deformation and failure in a better way. And we'll do so primarily with pictures and videos. Now, to keep things into perspective and avoiding too much thinning out, I will focus mainly on 3 modes of testing: uniaxial tension testing that we have already seen, biaxial testing, and some special cases for component testing. Let's move on to biaxial tension tests, which are also multi-axial tension tests. A biaxial tension test is run on a custom machine which somewhat looks like this, that's shown in the figure. A sample is clamped from the sides and a semicircular punch deforms the sample from the bottom so that the sample deforms in the form of a dome, which is monitored by DIC cameras which are located on the top of the press or on the top of the sample. Now this type of test can be done without DIC. However, the ISO standard recommends the use of DIC as the strain measurements and the repeatability that can be achieved with DIC cannot be surpassed by any other technique. I'll quickly run a video which shows a biaxial or a balanced biaxial test and 3 virtual sections drawn on the sample which show the strain evolution. The right hand side top of the plot is the force experienced by the punch when the sample was being deformed. The bottom right is the major strain along these cross sections drawn on the surface of the sample. I'll run this video again. So this shows as the sample deforms, the strain accumulates in the center of the sections or the center of the sample, and then the sample starts localizing and it fractures. So this kind of test truly shows the power of DIC, and there is no other technique that can represent the true nature of the material in this way. Now, the next test that I'll be talking about is a hydraulic bulge test, which is again a very special and customized test. The setup somewhat looks like the previous test, where the sample is clamped on the sides. However, there is no mechanical punch deforming the sample here. This test is a hydroforming test, and the deformation happens using a pressurized fluid that comes from the bottom and again deforms the sample in the form of a dome. Look at a video of a 4 micron copper foil when it is undergoing a balanced biaxial deformation. So this type of deformation on a material which is 4 micron thick can only be achieved with a non-contact extensometer or a non-contact metrology tool which does not interfere at all with the sample itself, because the sample in this case is so fragile that any kind of interference or any kind of disturbance on the sample will affect its properties and literally damage the sample. Now let's look into how does DIC work before we look at some other examples. I'll be talking about some high-level details on how a DIC algorithm really works. For that, first we need to understand the workflow of DIC. So for DIC to work, there has to be a good amount of contrast on the surface of the sample or whatever body we are trying to monitor. For that, the samples are painted in black and white speckle pattern as shown in the images on the left hand side. Now, as the deformation happens or the test progresses, the cameras record images of this test sample at a known frequency. For example, in this set of images shown here, the camera is recording at 10 frames per second, and therefore we have 1 to 500 images for a total of 50 seconds. Now these acquired images are used by a DIC program, and this DIC program spits out a full field strain contour and other tabulated data that can be used. Now we need to know, or we would like to understand, how this DIC program is actually working. So for that, we need to understand what is an image. So an image is basically a two-dimensional array of pixels. Each cell of that array represents a number. I'm specifically talking about gray value images, where Each number from 0 to 255 corresponds to a gray value. 0 is completely black, which means no light, and 255 is completely white. So an image on the bottom, which clearly shows 8 here, is actually a combination of numbers from 0 to 255. Wherever there is white and actually 8 is written, there is a number that's closer to 255, and wherever there is black, there is a number close to 0. That's how a computer understands an image, basically a gray value image. For other types of images, example a color image or HSV RGB image, there are other codes, but DIC algorithms typically work on gray value images. So that's what we'll focus on today. Now, it is impossible for DIC to track every single pixel. Therefore, the image of the test sample is divided into a set of points using a grid, and these grid intersection points behave like a mesh. Now this mesh is actually a DIC mesh, and the distance between the two nodes or two intersection points is called as mesh size. The denser the mesh size, greater the accuracy is, but slower the computation is. Now around these mesh points, we create a group of pixels called as subsets, and these subsets are arbitrary shapes. They could be squares, circles, triangles, hexagons, whatever, any geometrical figure that can have a centroid can take the shape of a subset. In this example that I have shown here, we have a square mesh and a square subset. So what DIC does is, it tracks the group of pixels inside a subset, and it basically latches onto a subset and tracks how that subset moves in 3D space in case of a 3D DIC. Now, when we know how a subset is moving on the surface of the sample along with the different images, those displacements of the subsets can be converted or resolved into x and y coordinates on the sample itself. Now these xy coordinates on the sample, in other words, give the translation of those local points or the mesh points on the sample itself. Now these displacement results that are coming from the mesh form a discontinuous map of displacements on the sample for all the points in the DIC mesh. Now these discontinuous maps are then interpolated to generate continuous map of displacements. There are various interpolation methods that are available in a DIC algorithm to use. Some are more accurate, but some are faster, so there is a trade-off there. Now, once we have a continuous map of displacements in the x and the y direction, these displacements are then differentiated to give strains, velocity, and other derived quantities. So that's in a nutshell how digital image correlation algorithms work. Now let's look at some creative applications of DIC, because DIC is not just about material testing. So let's see how DIC is used for testing automotive components. This is a typical example that I wanted to share. It is a rocker arm of an engine, and I was given this component to do some low cycle fatigue testing on it, and basically I had to develop an apparatus and take the sample from 0 to 10 kilonewton for countless cycles and see when it breaks. So this was the setup that's shown in the image. And I'll quickly go to a video that was one of the outputs of this test. So on the right hand side is the force when it is going from 0 to 20 kilonewton before it drops and then picks up again. So this video is showing one cycle of that fatigue test. So on the left hand side strain contour, we see that there are several points or points of displacement that are marked here. So that's one of the biggest advantages of DIC, that you can create a virtual extensometer or a point measurement on the surface of the sample in the post-processing phase. So there are virtually infinite number of extensometers available on the sample to be put to measure the strain at wherever location or whatever location you want to measure it at. So the bottom right plot is showing the strains at 5 points that were marked, that were the critical locations to the customer, and that's how DIC beautifully captured the strains on the surface of this rocker arm. Now this is again an amazing example to show the true power of DIC and the kind of applications it has been put into. So this video is from NASA Langley Research Center. What NASA wanted to see was the deformation on this fuselage of a space shuttle when it crash lands on another planet or the space station or whatever, wherever. So I'll run the video which shows that when the space shuttle lands, and by the way, this is a very high speed test and the DIC video was slowed down to show the deformation. See, the aircraft is spectral patterned, and as it lands, the nose has the maximum amount of strain and fractures first, and then the backside, the tail of it. So this, in this one, the touch point had the maximum strain, and then the strain moved forward and then went back to the tail. So all in all, these kind of tests give out a qualitative output on how the deformation would be, and also a quantitative output that can be used to match the finite element simulations that the engineers been running. This brings me to final remarks. So now we know that DIC is a really powerful tool, but which DIC is best? What should we buy? So there are many commercially available DICs, all are good. Some are better suited for material testing, some are better suited for other application. However, there is a tiny problem here. The commercially available DIC systems are extremely expensive. A simple 2D digital image correlation system would cost no less than $45,000. And if you want to buy a 3D or a stereo DIC system, which is a set of 2 cameras, it would go to at least $80,000. That's a problem, but not. Because we can build a DIC by ourselves. The only hardware that we need for making a 2D digital image correlation system is an off-the-shelf CMOS camera. Higher the resolution is better, of course, and even a phone camera works. The second thing that we would need is an additional light source, because the DIC images are always better when they are flooded with light. They are always light hungry, I would say. The third thing that we need is a scale bar, which means when we are clicking the image of an object, we need to have a correlation between how many pixels in the image actually correspond to what physical length dimension in the physical world. That would give it a perspective. And the last and the most important thing is a software, which is the DIC computation code. We'll talk about the DIC computation codes in the next slide, and I've left a very useful resource on the slide here. The IDIC, which is the International Agency or the organization for DIC, they have really good resources on their website, and their website is idics.org. Going on to the DIC computation codes, I would say, in my opinion, the best commercial program is GOM Correlate, which is made by a German company, GOM, who are the industry leaders, and they provide their correlation code GOM Correlate version 2016 to 21 free of cost for the users to try. And of course it has some limited capabilities because it's a free version, but still it's very powerful for the beginner users. For research purposes, there are many powerful non-commercial codes that are available on GitHub and other code repositories. So these codes are mainly in MATLAB or Python, some are in C++. The most powerful ones that I have tried myself during my PhD are NCOR, DICE, and pre-DIC. Now, the final takeaway is, I think everyone should start using DIC. It's so powerful. So for the teaching staff who are associated with any college and are on this in this conference, I would say that with some effort, the state-of-the-art technology can be added to the lab facilities at minimal expenses, and the quality of research can be improved drastically. Also, some real-time experiments can be demonstrated to the students in the classroom. For example, I've given an example of a cantilever beam. It was a very quick test that I did just for this presentation to show that if a cantilever beam is loaded on one side, you can process the two images with the IC and show that there is compression at the top and then tension at the bottom. Very simple, very cool stuff that will keep the students interested and also enthusiastic about new technologies. And for the students, just feel free to use this technology for your final year projects or research projects, whatever you're interested in, because it's an open playground for creative applications of this amazing technology. With this, I would like to thank everyone, and I have my email ID on the screen. So for any follow-up questions, please feel free to reach me. Thank you.